Okay, so now we're going to discuss the integral test and P series. Take a look at Larson and Edwards Calculus Ninth Edition. This is Theorem 9.10, the integral test. And it says if f is a positive, continuous, and decreasing function, so we have a function f that is positive, continuous, and decreasing for all x's that are greater than or equal to 1. And also, an, which are the terms of my series, equals fn for each n. So for all values of n, the functional value is equal to the value of the term of the series. Then, the series, the sum of the series, or sorry, the series, and the integral of f of x dx either both converge or both diverge. So this is a test for convergence, and it can also prove that a certain series diverges. All you have to do is find a function that matches your series at all integer values of the independent variable. So let's see. Let's take a look at an example. All right. And the example that I want to look at is the sum from n equals 1 to infinity of, let's see, this is going to be n over n squared plus 1. N divided by n squared plus 1. So let's make sure that all the criteria are met here. The first thing is this has to be positive for all x greater than or equal to 1. And the numerator is positive if x is greater than or equal to 1, and the denominator is always positive. So this is definitely positive. And continuous, well, this is a rational function or rational expression here, and it would be there would be a discontinuity anywhere where the denominator would equal 0, and this denominator does not equal 0 for any real number because we're squaring a number which is positive and we're adding 1, so we can't get 0 there unless we use uh, non-real complex numbers. So not only is it positive, but it's also continuous. And then we want to see that it's decreasing. Well, it's kind of easy to see here that this numerator is not moving as fast as the denominator because the denominator is squared. So this thing is always decreasing. It's getting smaller because the denominator is getting large faster. But you can always use the first derivative test also. So let's take a look at a function that matches uh, with the terms of this series. That function would be called f, and it would just be x over x squared plus 1. So this function is the same as that, as the terms of that series over there. And what we want to do is we want to find out if the function is decreasing. So we can use the first derivative test, and we can take the first derivative of this function. And let's see, the first derivative is going to be, well, you can use the quotient rule, so it would be the denominator times the derivative of the numerator, which is 1, minus the numerator times the derivative of the denominator, which is 2x, all divided by the denominator squared. And let me see, this seems to yield, we have x squared, excuse me, sorry. We have x squared and we have minus 2x squared. These are going to yield a negative x squared, and we have a positive 1. So the numerator is 1 minus x squared. And the denominator, well, we can keep that as x squared plus 1 squared. So the critical numbers. Well, the denominator cannot equal 0, but the numerator can. The numerator equals 0 if x is equal to either 1 or negative 1, right? So the critical numbers are 1 and negative 1. 1 and negative 1. All we really are concerned with is what happens to the right of 1, because in our theorem 910 over here, it says that it has to be decreasing for x's that are greater than or equal to 1. It turns out that 1 is one of the critical numbers, so we just are concerned with the interval from 1 to infinity. So we're concerned with this interval over here. Right, so what we're going to do is we're going to test a point on that interval into the first derivative here to see whether the function is increasing or decreasing. So I'm going to plug in the number 2. So I'm going to find the f prime of 2. And the f prime of 2 is, let's see, that's going to be 1 minus 2 squared over 2 squared plus 1 squared. So that looks like it's going to be, well, that's 1 minus 4 over, that's 4 squared is, 2 squared is 4, plus 1 is 5, 5 squared is 25. At any rate, this is negative, which says that the function is, the derivative is negative here. So the function would be decreasing on this interval. We know that the function is decreasing on the interval from 1 to infinity, which is exactly what we need to use the integral test. Okay, so now we're ready to actually use the integral test. We've proven, excuse me, we've proven not only that the function is positive, we've proven that it's continuous, and we used the first derivative test to show that it was always, that it was decreasing for x's that are greater than or equal to 1. So for all x's greater than or equal to 1, we have it's positive, continuous, and decreasing. Now, what we want to do is we want to integrate this function from 1 to infinity. So we're going to integrate the f of x from 1 to infinity. The f of x was x over x squared plus 1. And if this integral converges, then so does the series. And if the integral diverges, then so does the series. That is the point of theorem 9.1. Okay, so let's go ahead and evaluate this integral. Now, by definition, this is an improper integral, and it's equal to the limit as b approaches infinity of the integral from 1 to b of x over x squared plus 1 dx. All right, so to evaluate this integral, let's see, this one looks like a u sub. Um, I would need 2 for the derivative of the denominator, and that would make me have to put a 1/2 in the front here. And then this becomes a u substitution. If you let u equal x squared plus 1, then du would equal 2 dx. And you could rewrite this integral, and the substitution here would be, this would be u prime, or du over u. So when you actually did your integral, you would get that this is the limit as b approaches infinity of 1/2. The 1/2 would still be here. But this would be the natural log of u, which would be the natural log of x squared plus 1, natural log of x squared plus 1. And this would be all evaluated from 1 to b. All right, so we'd have this thing. And let's see. So from this integral now, we're going to plug in our upper and lower limits of integration. So this is going to be the limit as b approaches infinity of 1/2 of, this is going to be now the natural log, the ln, of the absolute value of b squared plus 1 minus the natural log of the absolute value of 1 squared plus 1, which is 2, closing this up. All right, now, when we go inside here, this is the limit as b approaches infinity. B is the variable left over. This is just a number, the natural log of 2. But the natural log of b squared plus 1, if b goes to infinity, well, this entire term goes to infinity also. So we have infinity minus a constant multiplied by 1/2, which is just infinity. So it turns out that this integral diverges. This integral diverges, which means that our original series, this series right here, also diverges. Okay, now let's take a look at one more example here. All right, let's get rid of this. I want to take a look at this example here. I'm going to look at the sum from n equals 1 to infinity of 1 over x, oops, not x, 1 over n to the power of p. All right, now I'm going to try to find which values of p this converges. For which values of p. So I'm trying to find out which values of p this series converges for, if any, if any. All right, so I'm going to try to use the integral test to do this. Since we just learned the integral test, I'm going to try to use the integral test. So the f of x would equal to 1 over x to the power of p, where the variable here, the independent variable, is x. So let's see. I want to prove, I want to see use the integral test here. I want to show that this thing is always positive. Well, the numerator is positive. The numerator is just 1. And the denominator, if x is greater than or equal to 1, the denominator will also be positive, because any number greater than or equal to 1 is positive, and if you raise it to a power, you'll get a positive answer. So it's always positive, this function f. Let's see, is it continuous? Well, the only discontinuity here is if x is equal to 0. So x being greater than or equal to 1 means this thing is continuous everywhere above 0. So it's definitely continuous for x is greater than or equal to 1. So it's continuous. And then you just have to show that it's decreasing. Well, it's 1 divided by powers of the, it's 1 divided by integers raised to the power of p. So let's see um, where this would be, or if this would be decreasing. We can always use the first derivative test. So the first derivative test, let's take the first derivative of this. F prime of x would then be equal to, well, this, the original function, is equal to x to the negative p. So to take the derivative, I'd multiply by negative p in front, and I take 1 away from negative p. So I get this. This would be the derivative. And to find the critical values, I would set this equal to 0. And let's see, negative p. And then let's write this as x to the negative p plus 1 power. Let's factor out the negative 1 there. All right, so here we have it. This is the derivative set equal to 0. This would be, uh, the critical values here would be 0, because if x is equal to 0, then this is either equal to 0, or if this gives you something negative, it would be undefined actually. So the critical value here is 0, is a critical number. So once you have the critical number, well, we're only concerned with x's that are greater than or equal to 1 anyway. So all we have to do is take a number greater than or equal to 1, or actually, we can choose 1 if we wanted to, because on that entire interval to the right of 0 is going to have the same behavior, either be increasing or decreasing. So we can actually find the f prime of positive 1 here, and that's going to equal negative p to the 1, or times 1 to the negative p plus 1 power. Well, this is 1 to a power. It doesn't matter what the power is, that's just going to be 1. So this is equal to negative p. So the f prime of 1 is equal to negative p, which means on the interval from 1 to infinity, actually on the interval from 0 to infinity, ah, this thing is going to be decreasing. So we proved that it's decreasing, and that means that we can apply the integral test, because now we have that the original function here is not only positive, it's positive, but it's also continuous on the interval from 0 to infinity, and we just proved that it's decreasing on the interval from 0 to infinity with the first derivative test. Now, what we need to do now is actually apply the integral test. The integral test says either both of these converge or diverge. So I'm going to go the integral from 1 to infinity of the f of x, which is 1 over x to the p power. And we're going to look at this integral. All right, so now to do this integral, we'll look at the definition, which says that this is the limit as b approaches infinity of the integral from 1 to b of 1 over x to the p dx, which there are actually two cases here. There are actually two cases for this integral here. There's the case where p is equal to 1, and there's the case where p is not equal to 1. Let's take a look at case 1, where p is equal to 1. Case 1. Case 1 is p equals 1. Well, if p equals 1, then this limit looks like this. It's the limit as b approaches infinity of the integral from 1 to b of 1 over x to the p, but p is the number 1, dx, which means that this is equal to the limit as b approaches infinity of, well, the integral of 1 over x is the natural log of x. So this is going to be the natural log of x, and that's going to be from 1 to b. All right, so we have all of that. We have now just to plug in the upper and lower limits of integration and take the limit. So this is the limit as b approaches infinity of the natural log of the absolute value of b minus the natural log of the absolute value of 0. And this is just 0. Oops, of 1, sorry. The absolute value of 1, which is just 0. That goes to 0. But this one here, this is what we're taking the limit of actually. It's the limit as b approaches infinity of the natural log of b. Well, the natural log is an increasing function, so as b approaches infinity, the natural log of b will also approach infinity. So what does that mean? Well, coming back here, case 1, if p is equal to 1, then this integral diverges, which means that this series diverges if p is equal to 1. So if p is equal to 1, this series diverges. Now let's take a look at case 2. Case 2. Case 2 is where p does not equal 1. Now if p does not equal 1, p doesn't equal 1, then 1 over x to the p, when you do the integral, you're not going to get the natural log. You're going to actually be able to use the power rule. So let's go ahead and look at that. It's the integral from 1 to infinity of, this is going to be 1 over x to the p dx, where p is not the number 1, so we can actually use the power rule. Well, we can write the limit definition here, the limit as b approaches infinity of the integral from 1 to b of 1 over x to the p dx. And then this integral, like I said, we can just use the power rule, which says that this is going to be the limit as b approaches infinity of, let's see, now this is going to be, we're going to add 1 to this, which is going to be negative p plus 1. And we're going to divide by that, so it's going to be 1 over negative p plus 1, x to the negative p plus 1. And we're going to take this from 1 to b, and that would be the use of the power rule. So we have this now, which is equal to the limit as b approaches infinity of, let's see what this is. This is going to be 1 over, well, I can write this as 1 minus p, and I'm going to have b to the 1 minus p power, and then minus 1 over 1 minus p, and then it's going to be 1 to that power, but 1 to that power is just going to be 1, so that would be that term. Okay, so here we have it, and all we need to do now is calculate this limit. Well, there are two cases for this limit, actually. If b is a number greater than, or sorry, not b, if p is a number greater than 1, then 1 minus that number would be negative, and this factor would actually be in the denominator of the fraction. So let's take a look at that. If p is greater than 1, if p is greater than 1, then what you have here is this. This is the limit of, as b approaches infinity of 1 over 1 minus p, and then this would be in the denominator because it would be negative. This value would be negative, so it would be b to some power. Let's call it y, for instance. But that power would be in the denominator because it would be negative. 1 minus p would be y. Y would equal 1 minus p, but y would be a negative number. So it would be in the denominator down here. And actually, I guess negative y would be 1 minus p, so you can bring it down and it would be positive y down here. But anyway, at any rate, when it's in the denominator, that means this entire thing goes to 0. 1 minus p. It means the entire thing goes to 0, and we get the answer to this to be negative 1 over 1 minus p, which is the same as 1 over p minus 1. You just distribute the negative to the denominator here. The 1 becomes negative, the p becomes positive. So if p is greater than 1, then not only does this thing converge, but it converges to 1 over p minus 1 here. And the second case here, or I guess this would be a third case because we're already looking at a second case. If p is less than 1, if p is less than 1, then this term is positive, and this thing explodes because you have the limit as b approaches infinity of 1 over 1 minus p 1 over 1 minus p, and then this b to the 1 minus p power, well, 1 minus p would now be positive, and then you get infinity to a positive power, which is infinity, and this thing would be infinity, which means it diverges. So the only case where this thing converges is where p is greater than 1. The only case where this kind of series will converge, the only case where this series converges is where p is greater than 1. So if you see a series like this is actually called a p series. And a p series only converges when p is greater than 1. And that is actually theorem 9.11. Let's take a look at theorem 9.11 over here. So let's go back to our Larson and Edwards ninth edition. Go to the next page here. And here we have uh, P series and harmonic series. Wrong page. Next page, sorry. Yeah, P series and harmonic series. All right, so here we have it. A type of series that has a simple arithmetic test for convergence. A series of this form. The sum as n from n equals 1 to infinity of 1 over n to the p power, which is what we have on the left side here. And it looks like that. It's called a p series. Now, if a p series has the value p equal 1, it's called a harmonic series. And the harmonic series is just the first one we explored where where p was equal to 1. Case 1 here, if p is equal to 1, and we said that kind of series diverges. So this series diverges. If p is equal to 1, the series diverges because the limit here is infinity. That's called a harmonic series. The harmonic series is a p series where p is equal to 1. And let's see. That is theorem 9.11 now. Theorem 9.11, the p series. So it says if you have a p series, this is how you know if it converges. A p series converges if p is greater than 1 and diverges if p is a number between 0 and 1, including 1. And we just proved that. We just actually saw that was true by the integral test. So now if you identify something as a p series, you can immediately see if it converges or diverges just by looking at the value of p. All right, so that is the discussion of p series and the integral test.